Associate at the Department of Biochemistry. Paolo has multidisciplinary background with specific interest in energy conversion and photosynthesis. His work is instrumental in studying the integration of biological and photobiological elements with physical components for direct generation of electric current, wastewater treatment, food production, and as a bio-environmental sensors. So I invite Paolo to present his work to us.
Thank you. Thank you. Hello, everyone. First of all, thank you to Priyanka for organizing and inviting. So I don't know how many of you have already come across with the concept of generating electricity using plants and photosynthetic organisms. Sorry, can you hear me? Yeah, okay, good. So during this talk, I will try to give you a generic overview on what I'm doing in order to achieve this goal. And also I will try to give you an overview of what we could actually use this system for, doing also comparison with classical solar panel. First of all, the other way around. So first of all, I want to do a distinction between, because in my title I said photosynthetic organism. So let's do a distinction between algae or microalgae and plants. I need to do this distinction because the two systems operate in a different way. So for the microalgae, we have published a few papers. For example, in this one, published no longer ago, we end up, well, the person in charge for this study, her name is Marin. She ended up doing something very, in my view, elegant. She ended up modifying a printer, and instead of using the usual ink, she's using microalgae for printing. And she's mixing this microalgae with a powder of conductive carbon. So in this way, she's printing the algae and the carbon together that we will work as an anode. I'll show you later on what I mean anode. So just for a visual understanding, this green tray is the print of the algae with the algae alone, and the gray one is the electrode. Actually, I brought with me, by mistake, on something that was printed by Marin about 2 years ago using algae. So if you want, you can have a look. You can pass around. So in my view, it's very remarkable that this was printed about 2 years ago and is still there. So not necessarily algae need to be a great ink for printing, but it definitely works. So we end up also publishing other papers based on algae. This one actually is a comparison of cyanobacteria versus the photosystem that operate inside of cyanobacteria. That another one where we build up the system within microchannels, and these facilitate very much the mass transport of ions. For this reason, by using this technique, we were able to reach a very high electrical output. And recently, I think this one came out no longer than a week ago, we end up modifying the surface of an electrode, making the surface very, very porous. In this way, the algae can colonizing every bits of the electrode. But we also end up doing some work generating electricity using plants. In this example, we were working with rice, and we have done a comparison between a rice plant with have you ever come across something called echinocloa? Echinocloa, for people working with rice, is a weed. Rice is a seed-free plant. Echinocloa is a C4 plant. And as you can see, they are really, really similar each other in a way that people that grow rice cannot spot echinocloa on the early stage, so they cannot remove it. But because it's a C4 plant, at some point it gets an advantage over rice that is a C3. So at some point you can see echinocloa that is not going to produce any valuable product taking over and compromising the productivity of your field. So, and we end up doing a couple of experiments, doing a comparison between rice and echinocloa. The taking home message of this one is, well, rice was generating electricity when the plant was growing, and then in the end, you don't compromise the productivity of your field. So in this way, you can have a bit of electricity, and then in the end of the process, you still have the grain, the rice. And more recently, we published a paper where we proved that we can produce electricity also from moss. This was the first example of this system operating with moss. So today, I'm not going to tell you too much about the algal system. I'm going to focus on the plant one. First of all, because we got one here, so you can also look around. Well, the grass is a bit tatty, but bear in mind, oh, maybe I should stay on the camera. But bear in mind that this was traveling from, well, from London to Milan. In Milan, I went to several schools to give talks, and then I took a flight to Delhi, and then I went to Goa, and then I came here, and all the time I was hidden in my bag. So, but I think it's still working. So later on, I can also describe you what the different parts are. But also the other reason, because I'll be focused on this, on the plant side, the project that we are going to initiate with Priyanka actually concern plants rather than algae. Although we might have a twist with algae, but the core is going to be on plant. So first of all, let's start with a very generic. I know that probably, guys, you have good knowledge of plants, so excuse me if I'm going to tell you something that you already know, but at least is a minimum introduction. To generate electrons through photosynthesis, first of all, you need a photosynthetic organism that is represented here by this nice and green leaf. Then you need a source of electrons. And a very good source of electrons for any photosynthetic organism. Okay, maybe I. So I got overexcited. Oh, okay, it's back. It's back. It's back. So the source of electrons is actually water. And then, of course, you need a source of energy to take in the electrons from water. And this process, as you know very well, is called photosynthesis, or more specifically, this process is the photolysis of water. It's the early stage in the photosynthetic activity. Is when this process occurs in thylacose membranes. I don't know whether you know where thylacose membranes are. Within any photosynthetic oxygenic organism, so we're talking about cyanobacteria, algae, microalgae, mosses, plants, there are these membrane called thylakoids. Embed into the thylakoids, so there are these two large photosynthetic complexes, the complex 1 and the complex 2. They operate together, and the main function is to harness light and use it to perform a charge separation. The charge separation then in photosystem 2 is actually used by the oxygen evolving complex to break water in protons, oxygen, and electrons. Protons are released inside the lumen of the thylakoids, and then later on can escape through an ATP synthase, and the electrons can go through the core of the photosystem, and then it can be passed through the photosynthetic electron transport chain to the photosystem 1, where, thanks to more light, can be sent to reduce the NADP to NADPH. This event is actually called the water photolysis, and is actually the source of electrons and protons for all our life. So the point is, how much, during my talk, sometimes I say electrons, sometimes I say electricity or current. Actually, it's not completely identical. However, electricity is a flux of electrons. So in order to have electricity, we need electrons. However, if we go electrons, not necessarily we go electricity, because we need to move electrons across two different points with two different potential. But by having this drop in potential and having electrons, we can generate electricity. So, first of all, because I told you that we can get electrons from water, but let's try to quantify how much electrons we can get from a glass of water. When I say glass of water, I decide to call it for 180 mLs. That, trust me, is probably more or less the size of that glass. The reason because I pick 180, it's going to be easier to do the calculation. So, if we consider the battery of my mobile, the battery of my mobile can hold up to 1,520 milliamps hour. Amps is the unit for measuring the current. 1 amp is 1 coulomb per second. The coulomb are the charges. They are telling you how many things with negative charge are inside of these. And because these amps is a coulomb per second and an hour is 3,600 seconds, we can calculate the total amount of coulombs or charges inside of this battery. That is about 5,500 roughly. So now we know how many coulombs are inside here. Let's try to calculate how many coulombs are here. So, by using 180 mLs of water, I use this 180 because the molecular weight of water is about 18. As the density is 1 gram, we can calculate that in a glass of water like this, there are 10 mole of water. In each mole of anything, there is a Faraday number of charges. This is actually called the Faraday constant. Therefore, by multiplying this times this, we can calculate how many coulombs are in this glass of water. That is about 1 million. And then if we divide by the number of coulombs inside of this battery, we can determine that in a glass of water, there are about 176 of the charges that are in this battery. So potentially, water is a great source of electrons. The trouble is, electrons in water are nicely and very organized in a very stable way with protons and oxygen forming water. So therefore, convincing the water to leave, convincing the electrons to leave the protons is not easy. But plants can do it. We said before, the water photolysis of plants is exactly the way to take electrons from water. So, I said could exactly because those electrons are not necessarily available. Let's move from could to can. So, by building up one of those systems, we can move from could to can. And we have operated this system with, this example is with moss. And we end up measuring the performance of the system. So this graph is actually called polarization curve. So in this graph, we are measuring, well, we are plotting current versus potential. Current are in milliamps and potential in millivolt. I don't want to stress you too much about this graph, but just to explain you what this line is telling you. When you have a battery, any battery, even the battery of my mobile phone, you tend to have two different ending points, normally called plus and minus. Before you connecting these plus and minus to something, there are no electrons moving. Therefore, the current, because remember, current is when electrons are moving, therefore the current is down to 0, and you got your maximum value of potential. Then if you connect plus with minus with something, you permit the electrons to move. And more you moving electrons, more you compromising your potential. Therefore is a trade-off. You need to choose between having a lot of potential but no current, or a lot of current and a very little potential. Later on, I'll show you an example where we were, where we deliberately decide to operate in a specific region. But in order to calculate how many electrons we can generate from this MOS, I decide to operate in this region. So when we got the maximum current. So in that region, we go about 50 milliamps per square meter. I report this data. This system is not a square meter, but anyway, I recalculate them based on square meter. So if we consider in an arbitrary way 1 day of operation, I decide 1 day of operation because more or less I need to recharge my mobile every day. So I said, okay, let's decide 1 day of operation. In 1 day, there are 86,400 seconds, 24 times 3,600. As milliamps are millicoulomb per second. So if we multiply these, we can calculate the number of coulombs that we can generate from MOS. That is this number. If you remember, this is the number of coulomb in this battery. So means 1 square meter of this system is almost stable, 0.8, so almost able to charge this per day. Of course, we need to take in account also the potential, because if we operate this, the potential is quite small. But this is a different. I will tell you about this a bit later. So, but in terms of electrons, 1 square meter of these should be able to provide a number of charges enough to charge up this battery. When I first approached this topic, I was very surprised that I'm able to generate electricity from plant, and I need to admit that I'm guilty. Because when I'm writing a paper, I try to say this is a new system or is a novel, because when you send something, a manuscript to a journal, you need to prove that you're doing something new. But in reality, generating electricity from plants, or more specifically, generating electricity from living organisms is actually not a new concept. The first person that ended up discovering, maybe we can have a long discussion, and I'm not sure that nobody really knows who was, but the first person that ended up publishing the generation of electricity from a living organism actually was more than 100 years ago. So this is the picture from the original paper. The paper was published on the Proceeding of the Royal Society in London. In 1911, the author at that time, the time was very frustrating because at that time I'm pretty sure there were other people working with Mr. Potter. I double check, he's not Harry Potter. But for some reason at that time, only the big professor, he was the professor, get the name of the paper. So we don't know who were the other people that are working and probably doing the job for Professor Potter. But something that intrigued me a lot, well, I'm not going to explain you too much about this, because to be honest, I'm very confused as well when I read the paper. Some of the parts don't make sense to me. But anyway, let's bear in mind that he was using a technology that for that time was very, very advanced. So then let's not be focused on this. So, Professor Potter in Durham University was professor of botany. And he did this experiment using yeast. And I found very intriguing on the fact that this guy spent all his life studying plants and ended up generating electricity using yeast. He never tried plants. And I mean, good for us because now we got something new to claim. But I don't know, I was very, very, very confused why building up all your career on plants and then don't try with this experiment. But anyway, good for us, good for us. So after spending a good amount of time telling you about this new stuff, maybe it's now time to tell you a bit more how it works. So, can I have it back? So, thank you. So let's start by just considering the plant. So we got our nice and green plant receiving solar light, water, remember the electrons, and also carbon dioxide, and the plant is sitting on the soil. So I like to say business as usual. And if you wait long enough, the plant grows doing photosynthesis. But while it's growing, some of the product from photosynthesis are actually released in the soil where the plant is living. And this product are actually called exudates. It's a mix of, depending from plant to plant, but typical exudate is lactic acid. This is a typical exudate from many plants. So why plants are exudating, are doing a lot of work to create some product and then dumping this product in the soil. They do that because they are trying to put together a sort of a trading with something living in the soil, that are the bacteria. They give this exudate, this rich organic carbon to the bacteria. And the bacteria say thanks generally by giving back some nutrients. Typical example could be some vitamins. So for the bacteria, the exudate is the energy that permits the bacteria to stay alive. If you are living in the soil, even a couple of centimeters under the ground, there is not too much oxygen, because here there is a 21% of oxygen, but when you go on the ground, not too much oxygen is able to get into the ground, especially if there is a layer of water. When you go organic carbon and you oxidize the carbon without oxygen, you end up doing a fermentation. So you got a problem that you need to find a way to dump your electrons and protons. So when you oxidize the exudate, you end up with electrons and protons, and you don't really know where to put them. If would be oxygen available, you can actually put them in forming carbon dioxide and water. But without oxygen available, you need to find a way to discard those protons and electrons. And if you got protons and electrons and you put together and you shake it with the right enzyme, you might end up with methane. Just this morning, Priyanka was telling me that one of your lakes was on fire. Which lake was it? Okay, probably what was happening was there were a lot of bacteria, I guess, generating methane, because they were operating, they were oxidizing organics without oxygen. This is actually a big problem, because, for example, from the paddy field, when we got millions and millions of plants of rice growing in this soil that is completely anoxic, we got generation of a large quantity of methane. And methane is 10 times more dangerous for the greenhouse effect than carbon dioxide. So potentially, from a paddy field where we grow rice, we generate a lot of methane. But there is a way to avoid this. There is a way to avoid the generation of methane. And if we provide a different way to discard electrons and protons. And this can be done by integrating two electrodes. So if we integrate something that is able to compensate for the protons and electrons, actually we can, without compromising the life of the bacteria, and without compromising the life of the plants, because anyway the plants will anyway give to the bacteria the exudate. The exudate will be oxidized to the bacteria to stay alive and probably give back something to the plants. The only thing that we provide is an alternative way to discard the electron and protons. So the two electrodes are, I don't know who decide to call them anode and cathode. And to be honest, I don't really have too much explanation about the name. The only things I want to tell you is the anode is the electrode that receive the electrons from the bacteria. Anode and cathode can be made by several different materials. What is important is they need to be electric conductive. Otherwise, they cannot be electrode. And because they are placed in soil, they also need to resist to oxidation from water. So we cannot just use, for example, copper, because after a little while, the copper starts dissolving, and also perhaps poisoning the bacteria, maybe poisoning the plants. So we need to use something that is stable. There are several different possibilities. A good material to work with is actually carbon. So in this example, if I gently remove this, this material that look like a tissue, a black tissue, is made by carbon. It's actually called carbon fiber. And is actually the electrode, the anode for this system. The plant is not going to like this, but if I pull this apart, I can actually see that the root of the plant starts forming a very tight relationship with the anode. It's exactly what I want, because what I want the root of the plant, and in this schematic are not shown, start forming a nice network around the anode. And of course, where there are roots, there are also the bacteria. Because the bacteria, they need to inject the electrons into the anode. How this is happening, it could take a bit of time to explain it. If someone wants to know it, later on we can have a discussion. I can even give you some publication to explain it. It's actually quite tricky to find a way to move electrons from the bacteria to the anode. So electrons meant to go to the anode, and protons will go to the cathode. The cathode will also require oxygen, because by having oxygen, then by receiving electrons from the external circuit, we can reform water. So the cathode in this in this system is actually based here, right on the bottom. It's based right on the bottom because we need to have access to oxygen. Remember, there is no chance for the oxygen to go through all the soil. So we need to provide an alternative way to feed oxygen to the cathode. And by having oxygen, protons, and electrons, we can reform water. If you remember, plants, they need to spend energy, that is the light, to split water. So splitting water required energy. Reforming water generate energy. More is better to say is isoergonic as a reaction. In fact, this drives all the process. One thing I want to tell you about these electrons and proton movement. Electrons and protons, they don't know where to go. So there are no like a signal to the protons to go to the cathode and electrons to go to the electrons to go to the anode. Matter of fact, there are ways to attract those species in one direction to the other, but normally if you implement this method, you end up spending more energy than you generate. So the only thing that we need to do is let them moving by diffusion. Diffusion is a spontaneous event. The problem is when something is moving by diffusion, could move in any possible direction. So potentially we can also have electrons going here and protons going in the other direction. So in order to make sure that is not happening, we need to implement some tricks. For example, the only way to combine protons, oxygen, and electrons and forming water is by having a catalyst. Without catalyst, when these three elements meet each other, without a catalyst, nothing is happening. Or actually, matter of fact, something is happening, but it's going to take so long that it's pretty much pointless. So if we don't put the catalyst here, and more importantly, we don't give oxygen, the protons that end up meeting electrons on this surface, they are not doing anything. So eventually they will probably end up diffusing somewhere else, and eventually they're going to diffuse here. But we have a problem that electrons might be able to reach this point, and then forming water here without having electrons going through the external circuit. Remember, the external circuit is where we put our mobile phone. If we want to charge a mobile phone, the mobile phone needs to go here. If we form water directly on this spot, we reach a situation where it's something called the internal short circuit. So the electrons are moving, but without charging anything valuable for us. But if we create a barrier here that is permeable for protons, but impermeable for electrons, then we go a situation where perhaps some electrons, when I say electrons, electron carrier, because electrons cannot float in water. You need to have a molecule or something that transports the electrons. So the electrons might get close to the cathode, but are not able to pass this membrane. There are several possibilities. A typical membrane that is used to do this job is called Nafion. Nafion was created a few years ago, I believe by mistake, but I don't want to. Now is made by DuPont. DuPont, this large company. And Nafion is able to permit the proton to go through, but not the electrons. So in this way, we can make sure that if there are protons going here, nothing is happening. If there are electrons going in this direction, yeah, they might get close to the cathode, but they never reach the surface of the cathode. By implementing this trick, we can ensure so that if there are electrons diffusing on the right direction, indeed we got electricity. These are all the components forming this device. Again, I think it's a bit boring taking you through all this part. There is in this publication, Anyway, it's written down here. If someone is interested, all these parts are well defined and detailed, so you can go and read it. Just you need all these parts in order to transform the concept that I explained you before in something real. Because sooner or later, someone of you is going to ask me to do a comparison between these that we can call a biological solar panel with a classical solar panel. So I decided to put some slides in order to approach this topic in order to avoid that. Anyway, someone is going to ask anyway. So let's do a comparison between a biological solar panel versus a classical or photovoltaic solar panel. So first of all, let's define the why a biological solar panel is not yet great. The current and the power output are not yet great. Compare a classical solar panel, a biological one is 10, 100 times less effective. And this is not a great news. I know very well. This is why we need to keep working on the factor that limit the performance of this system. Second, the current and the power output are not always reliable, and sometime, for example, the plant could die or the system is not working anymore, and then you need to do something to fix it. Generally speaking, you go to the shop, you buy this one, and you expect it works. If it is not working, you go back and you complain and give me another one that works. So it's more reliable technology. But of course, so far there are probably millions of people working on this technology, and I don't know how much money is being spent to develop this technology. We cannot say the same on this one. Another point is not very much a portable technology. So if you remember, I said to charge one of these, we need a square meter of these. This one is almost, I think, half kilo. So a square meter of these, probably we talk about above 100 kilos. So clear, I don't want to carry around 100 kilos just to charge my mobile. It would be completely stupid. So for this reason, I don't think this technology is a portable technology. But let's go to the good part. Why I think there is a good value of working on this and develop this technology. So first of all, this one generates electricity only when there is light. When there is dark, there is no electricity generation. This one generates electricity also in the dark, because you remember that what generates electricity in this system are actually the bacteria that get fed by plant. And the bacteria, of course, are metabolically active also during the night. Therefore you can have electricity also during the night. And for this reason, we can say that there is a sort of an internal capacitance. Means if there is a lot of sun, but you don't need electricity, the capability of this system is wasted. If there is a lot of sun and there is no electricity, in biological solar panel, it's not wasted, because they doing anyway photosynthesis. They accumulate exudate, and when you need it, and then you connect anode to cathode, you can discharge all part of the charges that has been accumulated. The second point is to build up one of those is not an easy job. You need a quite large and expensive facility. To build up this one is much easier. Actually, I was running a workshop no longer ago, like 3 weeks ago in school, and with kids, with all the parts, we were able to build up this system within a couple of hours. So building up this system is much easier and required a far smaller facility. And there is another great advantage. If you buy one of these, you take out the box, it's not working, you go back to the shop to complain. But if you buy it, you use it for a little while, and then it's not working anymore. Either maybe you go back to the shop, and the owner said to you, "I'm sorry, you break it," or "Sorry, is not under warranty." Or perhaps you buy it and you take it somewhere in the middle of nowhere, so there is no way to go back and change it. So if something goes wrong, you are just in trouble. There is nothing to do. With this one, with a bit of knowledge, you can actually fix it. In the same way that you can build it in a couple of hours, in a couple of hours you can fix it. And this is a great advantage, because with this one, you don't pump the local economy. Generally, people that use this one, they don't produce this one, they don't fix this one. They just buy from somewhere else. With this one, you can have someone in your local economy working for producing or fixing it. So it's a far more sustainable technology. Also, it doesn't deliver just electricity, because there is something growing here. This is a biomass. It could be a valuable product. For example, if you remember, if this would be a rice plant, you got electricity and then the rice. And with Priyanka, we're gonna try to treat wastewater. So it means we're gonna have the plant growing, electricity production, and some wastewater treatment. So we don't know yet how it's gonna turn up, but potentially is another outcome. So there are multiple products coming out from this. From this one, there's just one product, electricity. Also, and this is something that is always neglected when you go and buy this one, because you go and buy this one, they are telling you that this solar panel generates 50 watt per square meter. But these 50 watt of square meter are true only when the solar panel is tested under specific condition. As for specific condition, I'm talking about not only light, I'm also talking about temperature and humidity. When you put this on the roof of your house, the temperature is probably different from the temperature used for testing. Light, of course, changing all the time during the day. Humidity, of course. So, and of course, the pigments that are inside of this solar panel are not changing, because it's not alive, this solar panel. In this solar panel, the pigments are part of something that is alive. So the harnessing system could change over time when the conditions are changing. So this system is far more flexible than this. And finally, this could contribute to biodiversity, because in a system like this, you can have insects living, birds living, not necessarily in a system like this. And personally, also, I think it's more beautiful than this one. But this is on my personal judgment. So let me give you now some example of the type of signal, the type of current that we generate from a device like this. So back in Cambridge, Peter, one of my master students, I performed some experiment using 5 of those pots. These show you a typical example of the current that you can generate. I'm gonna take you through this graph. So first of all, okay, 0.25 represent time. Our hour, so means this is a full day. The yellow line is the light recorded during this 24 hour. This experiment was actually done in London, in the UCL, last summer. Actually, I think it's a September time. So you see the light in London in September, it starts coming in after 6 a.m. and it's dark, I think around 7:30, something like that. And of course, the signal of light is never very stable because we don't expect the light, well, the light of the sun generally is reasonably stable, but there are clouds, so there are any possible way. And this axis is telling you the light intensity. On this axis, we got the current output. First of all, if you operate with a solar panel, classical solar panel, the outcome of the classical solar panel will be tracking the light intensity. Look at how the signal is from this device. It's far more stable. And when you want to power something, you don't want something that move up and down because it makes quite difficult using this electricity. Whereas you prefer a more stable signal. Also, so in terms of light intensity, around midday, we got the most of our light intensity. In terms of current, we got the peak of current around probably 4:35. So there is a gap of around 4.5 hours between the gap of the top of the peak of light and the peak of current. And in some respect, this makes very much sense, because if you remember, light needs to be harnessed by the plant needs to do all this business of photosynthesis, produce some exudates, and this of course takes time, release the exudate diffuse in the soil, the bacteria need to pick up the exudate, oxidize the exudate, produce electrons and protons, and these electrons and protons migrate, actually diffuse. So this could take into account why there is this gap. But to be honest, for a practical use, that is not very much a big deal. Actually, in some respects, when the light is disappearing, you start having more current. That is not a bad deal at all. And as I said you before, look at the current when it's pitch dark and it's pitch dark. We still have current. So these are all advantages for operating with a biological solar panel. So in terms of when Peter operated these, end up finding that the generation of electricity was around 4,800 milliamps hour per square meter per month. Then there was a biomass generation of 160 grams. And also, if instead of water we use a wastewater, we might be able to generate water that is more clean or cleaner than the starting point. This is what we're going to try to do in the next weeks, month. So by generating electricity, the question mark that we can pose is, what can we do with this electricity? I don't really think we are going to power anything like a kettle. I personally think that if we want to generate a heat, either for warming up water or for cooking, in my view, we should use combustion. So indeed, biomass, let's generate biomass, let's having a tree, and let's burn a tree. In my view, of course, there are probably nice stools to do this job, but I wouldn't use electricity, no matter what. I wouldn't use electricity to generate heat. I'm telling you why. Forgetting about for a moment electricity from plant. So if you generate electricity from coal, you said that they might build up a new coal power station. So you got this lump of coal, you burn it, 70% of the energy of the coal goes away as a heat. Only 30% of the energy can be, roughly 35% can be used to generate electricity. Also, because the power station required additional energy to cool down, otherwise it's going to melt, you're going to spend more energy to cool down the power station. And then you transport this electricity across miles, and then when you receive it, you use it again to produce back heat, in my view, is not a nice way to use electricity. I still think that if we want to generate heat, let's burn something. But there are other possibilities to use this electricity. For example, maybe charging a mobile, charging a computer, we need probably between 1 and 10 watts, depending on the type of computer. This is why I say maybe. So far, probably we need something a large area for charging a computer with this system. Mobile, I would say that we are almost there. Definitely, if we go environmental sensor. For this reason, the project that we are trying to put together with Priyanka, the idea is to use the electricity that we generate from plants and wastewater to power the sensor that are monitoring the wastewater. So in my view, a very elegant system. So the system is treating water, generating some electricity, and use this electricity to check the water that was treated. A very nice content system. And by calculating the amount of energy that we need to do it, is completely feasible. So I'm now going through 2 case studies. The second one is a project that we want to do with Priyanka. The second one is actually a challenge that we just launched. And in matter of fact, if you are interested, you're very welcome to join it. Let me tell you a bit about this. So if you are in the forest and you want to operate an environmental sensor or a camera trap to take, I don't know, to record a population of animals, you need electricity. And not necessarily is always available. And not necessarily classical solar panel operate very well under the canopy when the light is not filtering off, is not very much. But of course, this is great for plant for a reason that I told you already. Plant is able to readjust the way that they harness the light. If there is not too much photons coming in, they can create more pigment, harness as much as possible. So for this reason, people working on the Zoological Society of London, they approach me and they ask me, can we actually build up one of these systems to power camera trap in the forest? And I said, well, I don't know, let's do some calculation. So it's exactly what we end up doing. So first of all, I asked them, how much do you need? And the answer was, we need 2,500 millicoulombs at 3.5 volts per day. This is not very much, and they can run the business with this amount of energy, because there is a company that creates a camera trap for them specifically with low energy consumption. So I said, okay, let's take some example. So this is the same graph that we see before. And before we were thinking, I do the calculation by having the current on this level. Let's thinking to operate on this point. If we operate on this point, we end up having around 500 millivolts and about 2 milliamps of current. As you see, I compromise the amount of current because I want to optimize the voltage. I need 3.5. Each system can give me 500. So in theory, with 7, I can do the job, but let's not risk. Let's having 10 in order to have 5 volts. So with 10 of these connected in series, we can meet the requirement in terms of potential. So in terms of current, if we are having 2 milliamps per square meter, means 2 millicoulomb per second per square meter, and this means that per day is this number, so 172,000 millicoulombs per square meter. We don't need that much, so the pot doesn't need to be 1 square meter. The pot, if we make the pot 30 centimeter in diameter, we end up with 708 centimeters square, and if we do the calculation, this is equal to 12,000 millicoulomb, we need 2,500 is more than enough. So it's feasible, it's actually possible. So therefore, instead of having us to create it, we decide to create a sort of a challenge. So the idea is, instead of spending money to do it, we got money from some sponsor. Specifically, we got £10,000. The idea is, I mean, I always believe that I'm not totally a silly boy, but not necessarily I'm the most clever person in this planet. Actually, for sure I'm not. Therefore, I said, instead to be me to create this system, we are advertising pretty much everywhere this challenge, and we are inviting everyone, can be an engineer, can be a designer, can be a scientist, to design something and send us a design, a plan. So on this website, you can find a link where you can upload your project. In a little while, we're gonna go through all the project and pick one and give to these people, probably it's gonna be a team, the £10,000 to create it. And then Alistair, the lucky one, is gonna take the prototype in the Amazon forest in Peru and test it. And if it's gonna work on the website of the Zoological Society of London, you're gonna see every day pictures coming out, taken by the camera trap, powered by the device that perhaps you have designed. So that would be the dream. The second case study, as I said, is something that we are going to start here in order to generate electricity in combination of wastewater. I'm not going to spend too much time to describe this. First of all, because it's not my cup of tea. It's something that somebody else says. Have you designed it? Or okay. So the only thing I want to tell you is there are 3 steps. In the last step, we can actually integrate a plant microbial fuel cell. So in this way, we can actually have on the last step the generation of electricity while we are treating wastewater. And these are actually the 3 prototypes on which we're going to integrate all the electrons. I believe these are the Terra Cotta, these are the materials. Probably they have been tested and not working in the optimal way. So all 3 are going to be operated with Terra Cotta. So I'm going to finish my talk giving you some example of outreach activity that I end up doing by using plant microbial fuel cell. So first of all, these are the several schools that I visit in person or I visit via Skype, on which I give talk about plant microbial fuel cell. Some are actually, this school is in Cambridge. This school is not far away from Cambridge, a couple of 100 miles, but the school actually quite far away from Cambridge. This is Czech Republic, US, Portugal, and I think this in Taiwan. So what I normally do, I give a talk similar to what I'm giving to you, and some of the school generally ask me, can we build up some of this? And depending on if we got time enough and we got resources enough, we end up sending to the school some of the components that they need to build up the system. Or more importantly, we send into the school a protocol to build up. And normally what I ask to the school is, please send me back if you end up doing something. And actually, lucky enough, I received something. So from the school in Taiwan, they build up the system, is here, and they perform some experiments. This is time and this potential. And although, I mean, only potential is not very informative, but anyway, I found the result very, very elegant because they end up generating different signal by using different light. So they expose the plant to different light, and the signal is different. I don't know if it's statistically different. I haven't performed any statistics, but in my view, it's quite interesting that the signal is indeed different. And more importantly, I didn't ask the school to do it. It's something that they decide to do it. This is proving that there is always someone more clever than you, more clever than me. So another school that come back to me with some result are the people in Portugal. And this table is giving you the result. This time they've done something more systematically. I love it. They put together 10 devices. These are the devices. The first one, they run it without plant. And this, as you see, the potential remain around 100 millivolts. And they run the other 9 with plants. And as you can see, the potential is a 400, 500, 300 millivolts. If you do an average, it's far bigger than. So they were proving that it's actually the plant doing a job. I don't know, I was totally in love for this result. I think they've done a fantastic job. But also we took this system or similar system to public events. This was in London about, gosh, the time fly, 7, 8 years ago. And we were powering a digital clock using algae. This is an algal clock during the Royal Society Science Festival. This is in Edinburgh. Again, we were powering this clock using 4 or 5 of these pots. Oh, sorry, this was inside the Edinburgh Science Festival. There is something called pint of science. Have you ever heard about pint of science? Maybe we'll come to India soon. Probably it's gonna be pint of. I don't know. It's called pint of science because in England, in Britain, people love beer, and you drink beer by pint. So it's a pint of beer. So the idea of people that created this activity was instead to go to the pub to drink a pint of beer, let's go to the pub and drink a pint of science. So let's get some knowledge in pub. So one per year, normally around May, sorry, they organize some talks in pub. And of course there is beer, because without beer people will not come to the pub. But also they invite scientists to give a talk. And this I was giving a talk talking about this technology in a pub. So this is what they call, for example, in Italy, they just introduced in Italy last year, and they call a glass of wine, glass of science, because we drink more wine than beer. So I don't know what would be the equivalent for India, but I'm pretty sure we can find the equivalent from India. This was very, very exciting. As a group of students, they create one of these systems operating with algae without my help, and they present it in Australia. So, and then they send me over, because they asked me the information how to build it. They did it, it worked, and they send me back the pictures. Unfortunately, not the data. Along to present this for in public event, something that is very close to my heart is also try to create an educational toolkit for school based on this technology. To do it, last year, I begged for some money from this pre-organization, and they were very kind, because overall they gave me £3,000. Again, instead of using these £3,000 to create an educational toolkit, I end up talking with those people. Those people are in Barcelona, in Spain, and they are not scientists. It's actually, what they do is architectural study and design. They are designers, they are architects. And there is a small independent university, and they do have a master student. And they put on this project four group of students. Each one, I think, were 3 or 4 people, 3 or 4 students for each group. I gave them a couple of talks explaining the technology, and the task for them was design something, and we're gonna give you the money to build it. And they end up creating 4 prototypes. All of them are interesting, all of them are very intriguing, but one, in my view, is more promising than the other. For this reason, I'm gonna tell you just about this one. That was called bio-bottle voltaic. It was called bio-bottle voltaic. It's a sort of an internal joke because the system was built inside a bottle, a used plastic bottle. I love it because, first of all, they use recycled material. Plastic bottles are unfortunately everywhere, so they were recycling. And also, they were using as an anode aluminium from recycled drinking can. When they were telling me about using aluminium, I was thinking, sure, I don't think it's a good idea. Probably this is going to kill the algae, because this system operates with algae. If you see, it's greenish because it's filled up with algae. Lucky enough, instead to tell them, no, sorry, don't use it, we try. And actually, algae like it. They grow very nicely. But more importantly, after a little while, the water is forming a layer of aluminum oxide on the surface of the anode. And this compromises a bit the conductivity of the anode. It is not great, but protect the anode for further oxidation. So we compromise a bit the conductivity, but anyhow remain still working, and the layer of aluminum oxide prevent that the anode disappear over time. The only thing they end up creating completely new is a new lid, 3D printed, where all the cathode, all the connections are embedded. All this information, how to build up the new lead, are available online on this website. So everything is open source. And more importantly, they create for us a few prototypes. And last summer, we got a summer student, and we end up performing some experiment. We submit a paper, and 2 days ago was accepted for publication. So now we're gonna have a proper scientific paper published on an educational toolkit created by master students. In my view, make a fantastic story. So I'm finishing off to say some thanks, because to do all this work, obviously I'm not alone. This is a group of people that I'm working with. The boss is Chris Howe. You might see this video. Hi, Chris. I also want to say thanks to quite a few people that work related with this project, not necessarily in my lab, but in different labs, either in Cambridge, in London, in other parts of the world. I want to say thanks to people that are not necessarily related with academia. Some of people are designers or linked with industry. Of course, I want to say thanks to the sponsor that pay for my bills. And of course, thank you for your attention.
Okay, so floor is open for questions. Is there biobattery? Another innovation is the development of space to generate technical. Have you thought about using it in rural areas where you need electricity for the bulb? I mean, going beyond sensors, sensors, we think about integrating it with, say, irrigation systems, where it might be useful. So, because at the moment, it seems like sensors are something which are very firmly rooted within academic and research. I want to see if there's a practicability of having tried looking at that and fix it actually really use it.
Okay, the answer is absolutely yes. So the next step that I haven't presented, but I might have a slide. Yeah.
I was wondering what is the cost of the carbon fiber? Is that the most expensive thing? And if so, could it be a constraint if really poor households want to opt for it?
Okay, let me first answer to the second one because it's easier. Carbon fiber, if you buy in England, per square meters costs around 15, 20 pounds. The translating round is 1,500, 2,000 round for square meter. But this is because you buy a small quantity. If you buy large quantity, the price decreases. But you can create yourself, because if you get some biomass and you burn this biomass without oxygen, you do a polarization, you can create your anode. So potentially you can do this without buying the anode. So the answer is yes, there is a cost. Potentially there is a way around it. At this moment, probably the more costly part is the catalyst. If you remember, to avoid to have the electrons recombine with protons and oxygen, you need a catalyst, and these remain a bit expensive. In fact, there are some people try to find cheap alternative to catalyst. Yes, we are really thinking to do what you said. We really want to create for people living in a rural area like a green hub surrounded of thousands of this system where you can go and charge your mobile or your computer or your light and go home and having light for the night. Definitely we want to do it. It's something that but I don't want to jump on this before. So far, this is all I'm doing, tiny. This would be very large, and also these people will depend on this. I don't want to give something that is not going to work. So far, this is working in the lab. Something that excites me a lot about what we're gonna do here with you guys. We're gonna move from something very small to something a bit bigger, from working in the lab to working outside. In my view, the result of those experiments will be an excellent indication to tell us whether we can move to this stage. So I really hope we're gonna do it soon.
The most promising is
So exactly, my point is what I said before. If you want to generate heat, burn something. This is my point, but maybe I'm wrong. Sorry.
Is there any size restriction? Means you're using multiple small things for scaling up or increasing. Means is there a chance? Means if you, for example, as Durba asked, if you do it in a farm level and use only one anode and one cathode, so whether the scale of the unit matters for collecting the charges.
So each unit, regardless the size, can be tiny or can be huge. In terms of potential, could generate no more than 1.1 volts. That is the theoretical limit. The theoretical limit is dictated by the anodic and the cathodic reaction. So the redox potential of the reaction occurring to the anode minus the redox potential of the reaction occurring to the cathode is giving you how many millivolts you can have from anode to cathode. I said theoretically is up 1.1. Practically, I haven't seen anything bigger than 800 millivolts. To be honest, generally I expect something around 500 millivolts. So this is one limitation that you need to take into account. So if you create a huge one, you go potentially a lot of current, but the potential is going to be 500 millivolts. Therefore, you need to consider how many volts you want to have and do a calculation and create a smaller one in order to collect in series. Indeed, if you need to choose between, assuming that you don't care about potential, assuming, if you create a very big one or many small ones that form the same area, I generally think that it's better small one connected together for several reasons. First of all, again, it's a matter of mass transport. Second, if you go many small one and one is faulty, you just replace it. If you go a big one and there is a problem, everything is not working. So it's something that you need to take into account. But to create many small one is more labor intense. Correct, exactly. So yeah.
What is the requirement for this system to find the fiber? Does it require as much water as those species of plants usually?
Okay, this is actually one of the limitations that we need to take into account. Okay, generally speaking, without water, it will not work simply because the plant will die, and this is quite obvious. Having said that, some plants tolerate drought. Some plants can grow in a, I don't want to say in a desert, but they can grow in an area where there is not too much water. Unfortunately, I don't think that situation is ideal for this system. This system operates better in places where, yes, indeed there is sun, but also water is not an issue. This is why I'm very excited to try the system in a raining forest in Amazon, because over there definitely there is sun, water is available, plants are very. And also I'm very happy to try here related with the lake, because always water will be available. And again, because you need water, this go back to the fact that this system tends to be quite heavy. You don't really want to carry around. So unfortunately, if water is not available, I would say perhaps consider other option, perhaps a classical solar panel. But water, yes, can be an issue. This is definitely one of the limitations. So let's say if you are in a dry area, this is not an option.
But even if it's seasonally dry, like
yeah.
get 6,000 mm, like some parts of it, get 6,000 mm a year, but only in like 4 months.
Yeah, exactly. So again, if you you need to take into account this condition and this limitation. Yeah. Okay. Yeah, but if you remember from this. So if you remember from this graph, oh, okay. So if you remember from this graph, this is actually the profile of current. I mean, I don't want to say it's a completely stable because it's not true, but is reasonably stable. This current was generated from a very well-mature system after a few months of operation. Initially, the system is, the current output is very unstable. So guys, don't be disappointed initially, but after a while, the system is getting more stable. And to be honest, yeah, there is variation between night and day. Probably there is a variation between if you use one plant to the other, but overall, I think the signal, the current is reasonably stable. Overall, if required, perhaps people could think to use a capacitor or a battery. I don't know. This is something that, in some respect, is a bit outside the aim of my study. In some respect, I try to generate electrons, and somebody else will find a way to store it. Sorry? Yeah, yeah.
One last question is, this seems like it seems like a perpetually low energy biobattery. Is there a limit to how much energy how much efficiency can one hope to achieve? And is there a possibility of increasing the efficiency anymore?
Yeah. So about 2 years ago, we published a paper when we have done some calculation, exactly try to answer this question. We have taken account many possible factors, and all these are at best of our knowledge. We think that we can reach up to 2–3% efficiency. That is not as efficient as a classical solar panel, but it's not bad at all. It's not bad at all. It means we can actually generate, I think, if I'm not wrong, around 7 watt per square meter. That is a quite remarkable power output. And bear in mind that these calculations are not telling you the theoretical maximum, because we decided we don't want to calculate the theoretical maximum. Theoretical maximum generally are something that is true only when everything is optimal. We said, let's try to define a scenario, optimistic scenario, but realistic scenario. So the number I gave you is something that we believe that in the future we can achieve. And so far we are probably between 1 and 2 orders of magnitude from the optimal results. So there is a room for improvement. You're very welcome.